chapter 1 of grade 12 is about motion. To study motion, first we need to remember grade 11. In grade 11, you have studied motion in one dimension and motion in two dimensions. To study any type of motion, you need to know some quantities. First quantity that you have studied in grade 11 was position, which is the location of an object with respect to a reference point. After that, you have studied displacement and distance. After that, you have studied velocity and speed. After that, you have studied acceleration. Position is the location of an object with respect to a reference point. So you need to have a reference point to start the measurement. Whenever you have a change in position, you have displacement. So displacement is simply change in position. Change in physics is delta, position is x, which is equal to x final minus x initial. We have two other definitions for displacement. One of them is the shortest possible path, or a line is drawn from x initial to x final, and the length of that line is called as displacement. Distance is the total traveled path. If we have an object that moves from x initial to x final in a time interval, so velocity in physics is defined as the rate of change in position. So whenever we have the rate of, it means whatever comes after it is divided by delta time. So now we have velocity, which is the equation for the average. The rate means it is divided by delta time. Change means delta. In position is x, so this is divided by delta time. So delta x over delta time, and the unit is meter per second. Simply, it describes how quickly an object moves. And remember that velocity is composed of two components, which are magnitude and direction. The magnitude has a name, which is called as speed. So whenever you see speed in any question, it means the magnitude of velocity, which is the distance divided by time interval. The unit is again meter per second, and so on. The next quantity that you have studied in grade 11 is acceleration. Acceleration is the rate of change in velocity. Since it is the rate of change of velocity, acceleration will be equal to something divided by delta time, because it starts with the rate. So this one is divided by delta time of change of velocity. So I will write delta V in the numerator, and the unit will be, delta V is meter per second, delta time is second. It will be equal to meter per second times 1 over second. It will be equal to meter per second squared. So the unit of acceleration is meter per second squared. Remember that whenever you have a change in velocity, you have acceleration. So acceleration means change in velocity. Let's say that V initial is equal to meter per second. After 1 second, it becomes 5 meter per second. After another second, it becomes 8 meter per second. So every second, the velocity has increased by plus 3 meter per second. That is the meaning of acceleration. As you see, there's a change. This change is 3 meter per second every second. The acceleration is plus 3 meter per second squared, which means that the velocity increases by 3 meter per second every 1 second. Let's talk about the difference between constant acceleration and zero acceleration. If there's no change in velocity, acceleration is equal to 0. There is no change in velocity means constant velocity. So zero acceleration means constant velocity. What about constant acceleration? Means the change in velocity is constant. So we have a change, but the change is constant, like the example we've seen a moment ago. Okay, why this is special? Because when acceleration is constant, we can say that the average velocity is equal to V initial plus V final divided by 2. We can only and only write this equalization if the acceleration is constant. At the same time, the average was equal to delta x divided by delta time. Now I can cross multiply this and I will get the first kinematic equation, which is delta x is equal to 1 over 2 v initial plus v final times delta time. The second kinematic equation comes from the equation of acceleration itself, which is v final minus v initial divided by delta time. Cross product both sides and you will get v final is equal to v initial plus acceleration multiplied by delta time. So this one is actually the equation of acceleration, which is saying that v final minus v initial divided by delta time. It only has been rearranged. The third equation is a little bit tricky, which starts with a delta x will be equal to v initial multiplied by delta time. Now, how do I remember that there is a delta time here? Look at the units. The unit for delta x is meter, or the unit of v is meter per second. So I need to multiply by delta time, which is second, to cancel the seconds, and I will have meter alone. If you pay attention to the first equation, I have a delta x and I have a 1 over 2. Now I have a delta x. The second equation also have a 1 over 2, but it is in the second part. And we know that there is an acceleration here. But again, some students may forget if there was a delta x or delta time here. There's a delta time, but the delta time must be square. How do I remember this as square? Look at the units again. The unit of acceleration is meter per second square. So I need to have meter alone, so I need to get rid of the second square. Multiplied by the second square will be the delta time square. The last equation is v final square, which is equal to v initial square. Since that's square, that's also must be square. We have a 2, so we have a 2 here. It is not 1 over 2. We have acceleration. But how do I remember that it is always delta x here? Again, look for the units. So this is meter per second, but both are square. So the unit of acceleration is meter per second squared. As you see, I need to have the meter to be squared too. So meter multiplied by meter. The quantity that has the unit of meter is delta x. That's how I remember there is always a delta x in the fourth equation. How about using all these four kinematic equations? If you pay attention to every equation, there's a missing quantity in each of them. The first one, the missing quantity, is acceleration. In the second one, there is no delta x. And in the third one, there's no v final. And in the last one, there's no delta time. So if you couldn't see acceleration in the givens or in the unknowns, use the first one. If delta x was not given or it was not required, directly use the second one. If it was the v final that was not given and it was not required, use the third one. And if delta time was not given, it was not asked or required, either use the last one. So these are the basic quantities that you need to define any type of motion. In grade 12, in chapter 1, section 1, you'll study circular motion. Any object that moves in a circular path has or is in a circular motion. We also have rotational motion. Any object that rotates or spins around itself is in rotational motion. In both rotational motion and circular motion, we have an axis. The difference between them is that the axis in circular motion is outside the object and it is at the center of the circle. It is at some distance from the object, which is the radius. The axis in rotational motion is on the object. It passes through the object actually. It doesn't necessarily need to be the center exactly. It can pass through any point. Here the axis is perpendicular to the object, but here the axis is perpendicular to the circle. So why are we talking about rotational motion if the chapter is about circular motion? We talk about the rotational motion because if we choose any point on a rotating object, it will follow a circle. Let's have an example, a Ferris wheel, and let's have some cabins on the first wheel. The first wheel is in rotational motion, and that is actually the center of the first wheel. But if I choose a cabin, I will see the cabin will follow a circular path. So the cabin, or any cabin actually, cabins are following a circular path. So the cabins are actually in circular motion. So regardless of the shape of the rotating object, every point except the axis of rotation follows a circular path. So every point is in circular motion. So we need to know what a circle is. Let's remember some properties of a circle from mathematics. Every point has same distance from the center. This distance is called as radius. From one end to the other end called as diameter, and diameter is equal to 2 times radius. So you can say that radius is equal to diameter divided by 2. The distance around a circle like that is called as circumference. Circumference is c, which is equal to 2 pi r. We have an example which is saying that a car is moving in a or on a 3.25 kilometer circular track. Please remember this when the time comes. So what is this 3.25? It is the distance on the circular track, which is actually the circumference. So this is equal to 2 pi r. This information will be given to you to find the radius. Another property of a circle is an angle, and until now you have studied revolution and degree. If you complete one cycle, it is one revolution. For revolution for a complete circle, or one turn, one times. If you complete the circle one times, these are all indications for the theta in revolution. For a complete circle, it is 360 in degrees. And if you have half cycle, you will have a half circle, half turn, and the theta in degree will be 180 degrees. You can say that the travel distance for a complete circle is 2 pi r. For a half circle, it is only pi r. A portion of a circle is called as arc. Arc is a portion or a part of a circle. Always remember that the arc is the traveled distance. The symbol for arc is S, but for arc length it will be delta S. So now we have radius, theta, and arc length. In mathematics, there is a relation between all these, which is saying that theta is the arc divided by the radius. But when we look at this equation, we encounter a problem, and the problem is that the unit for distance is meter, the unit for radius is also meter, and they will cancel each other, so there will be no unit. Since there is no unit, theta in this equation has no dimension. And I will name this as radian. So the unit for theta in this equation will be called as radian. We cannot use degree, we cannot use a revolution in this equation. How can we have 1 radian, and what is the theta in radian for a complete circle? Let's find both. Radian can also be defined as if the arc length is equal to the radius, then they will cancel each other, and theta will be equal to S over R. They will cancel each other, and we will get 1. What did we name that one as? We named it as radian. So when S is equal to, or when arc length is equal to radius, we have 1 radian. That is the definition of 1 radian. What about the theta of a complete circle in radian? We know that the S for a complete circle is equal to circumference, and circumference is equal to 2 pi r, and theta will be equal to S, which is equal to pi r, which is equal to circumference divided by radius, which is equal to 2 pi r divided by r. They will cancel each other and we get 2 pi. So this 2 pi is radian. One complete cycle is composed of one revolution. It is composed of 360 degrees. It is composed of 2 pi in radian. This pi, don't forget that, is 3.40. Now let's talk about how to convert radian to degree, degree to revolution, and vice versa. Let's have radian to degree and vice versa. The easiest way is to use the cross multiplication, which we'll be saying it as 2 pi in radian is equal to 360 in degrees. So theta in radian will be equal to theta in degrees. We will cross multiply both sides by each other and we get theta in radian multiplied by 360, which is equal to theta in degree multiplied by 2 pi. If you needed theta in radian, have it alone. If you needed theta in degree, have it alone. So to have theta in radian alone, we will divide both sides by 360. So I will be deleting them. So I will be saying that theta, if I have theta in radian alone, it will be equal to theta in degree multiplied by 2 pi divided by 360. You can simplify it further and say that theta in radian is equal to theta in degree multiplied by pi divided by 180. You can also say that theta in degree, if we have it alone, it will be equal to theta in radian multiplied by 360 divided by 2 pi. If you want to simplify it further, theta in degree will be equal to theta in radian multiplied by 180 divided by pi. Now you may wonder what is 1 radian in degrees? Let's find out. So you'll be using this equation, 1 radian multiplied by 180 divided by pi. It will be equal to 180 divided by pi. If you want to enter this number in the calculator, you will get 57.3 degrees. So you can say that 1 radian is equal to 57.3 degrees. Now, how can I convert radian into revolution and vice versa? Again, by using cross multiplication method. Let's have radian to revolution and vice versa. In radian, a complete circle is 2 pi. In revolution, it is 1 revolution. Theta in radian, theta in revolution. Again, cross multiply both sides by each other and you will get theta in radian multiplied by 1 is equal to theta in revolution multiplied by 2 pi. So it is that simple. Just delete the 1 and you will get the equation right away. If you want to find theta in revolution, simply divide both sides by 2 pi. So theta in revolution is equal to theta in radian divided by 2 pi. What about degree into revolution and vice versa? Again, in the same way. A complete circle is 360 degrees. It is 1 revolution. So theta in degree is equal to theta in revolution. Again, cross multiply both by each other. Theta in degree multiplied by 1 is equal to theta revolution multiplied by 360. So this is multiplied by 1. So now right away I get the conversion of revolution into degree. What about if I want theta in revolution alone? I will divide both sides by 360. I will get theta in degree divided by 360 and I will get the answer as theta in revolution. Now let us talk about angular displacement and angular speed and angular acceleration. If an object moves in a circular path, let's say the object is here exactly. In linear motion, we had a reference point. Here we have a reference line. So that's why it is called as 0 degrees. And let's say that this is theta initial of an object and it rotates in the counterclockwise direction. It will come to this point, which is its final angular position. So we will call this one as angular displacement. So angular displacement simply is the change in angle, so theta final minus theta initial. This is just as a definition. We will not use theta final minus theta initial at we don't have any example. We also have an arc length. As you see, this is delta S. They are always together. As a result, we can say that delta theta is equal to delta S over R. And in this equation, the angular displacement can only and only be measured and used as a radian. That's why we talked about the conversions a moment ago. We have two types of rotation. We have clockwise and counterclockwise. In the clockwise direction, both delta theta and delta S are negative. But in the counterclockwise direction, both delta theta and delta S are positive. So clockwise direction is like that, and counterclockwise direction is like that. This counterclockwise and this is clockwise. The radius is always positive. It can never be negative. Always remember that delta S is the traveled distance or traveled path. Now, if an object moves in a circular path, it will travel through an arc length of delta S in a time interval of delta time. At the same time, we have a change in theta initial and theta final. So we have a delta theta in the same time interval. So the object is moving through a distance in a time interval, so it has a certain linear speed. Linear speed will be equal to delta S over delta time, which is meter per second. It describes how quickly an object moves, and it also has another quantity which is called as angular speed. Angular speed can be defined as the rate of change in angular position. We said that whenever we have the rate, means something that comes after it is being divided by delta time. So the symbol of angular speed is omega. The equation that I'm writing is for average angular speed, which is delta theta divided by delta time. Delta theta was measured in radian divided by second. So the unit for angular speed is radian per second. So it simply describes how quickly an object rotates. Or you can also define as the rate of rotation. If the rotation is clockwise, all three, delta S, delta theta, and omega, they are all negative. If the rotation is counterclockwise, all of them are positive. In the angular speed, we have a very important topic, which is about constant angular speeds in our daily life. First one is the second hand of a clock, the hand that measures the second. We know that omega average is equal to delta theta over delta time. The second hand completes one cycle. Delta theta for one cycle is always 2 pi. It completes one cycle in 60 seconds. So this is the angular speed of a second hand, and it never changes. So we have to be able to find this one without any given information. The second one is the minute hand of a clock. Again, write the equation. The minute hand of a clock completes one cycle. One cycle is again 2 pi. It completes one cycle in 1 hour, which is 60 minutes. We have to convert into second multiplied by 60 second, and you will get the answer. The third one is the hour hand. Hour hand of a clock completes one cycle in how many hours? In 12 hours, because in 24 hours, the hour hand is completing 2 cycles. So we need 1 cycle only. It completes 1 cycle, which is 2 pi radian, in 12 hours. So I have to convert this hour into minute and into second. So this is hour, this is minute, and this is second. And another example is Earth around itself. Again, can be found by using the same equation. It completes one cycle. One cycle is again 2 pi. It completes one cycle in 24 hours. Convert into minute and convert it into second. So this is hour, this is minute, this is second. And you can also find the angular speed of Earth around Sun, which is a Wazari question. You can look at the book, question 6 of chapter review, which is asking how long does it take the second hand of a clock to move through 4 radian. How can we do that? It is a very simple and easy question. It can be solved in different ways. The first one is the classical way. The only given is delta theta, which is 4 radian, and the question is asking you to find delta time. The object is second hand of a clock. We know that omega of a second hand, we just found a moment ago, it was 2 pi over 60. So you have to have this information beforehand, which is equal to delta theta over delta time. Delta theta is given as 4, delta time is unknown, rearrange it, and delta time will be equal to 60 times 4 divided by 2 pi. That is the answer, which is equal to 38.2 seconds. What happens if they change the question? We have a simple, easy way to solve it. The first one will contain 2 pi if the given was in radian or it was asking to find delta theta in radian. I will use 360 if it was given in degree or it was asking me to find in degree. I will use 1 revolution if it was asking me to find theta in revolution. On the right side, write the time for 1 cycle. Next one, here either write the given theta or unknown theta. So if theta is given, time will be unknown. If theta is unknown, time will be given. And after that, cross multiply these by each other and you will directly get the answer. Let's solve it for the previous question. So it was given as a radian. So I will write the radian here. It completes 2 pi in 60 seconds. And 4 radian is given, time is unknown. I will cross multiply these by each other. Delta time is equal to 4 times 60 divided by 2 pi. And I will get the same answer, which was 38.2 seconds. Now let's talk about acceleration. If an object speeds up and slows down, it will have an acceleration. But if an object is rotating and is speeding up and slowing down, it will also have another acceleration, which is called as angular acceleration. So how can we define angular acceleration? It can be defined as the rate at which angular speed changes. So if the object speeds up or slows down, we will have angular acceleration. And the symbol of angular acceleration is alpha, which is divided by delta time because it starts with the rate of change in angular speed. Omega final minus omega initial divided by delta time. You can also write the delta time as t final minus t initial. It is in our book, but we don't use it. Now let's talk about constant angular acceleration and zero angular acceleration. So angular acceleration means change in angular speed. So whenever we have a change in omega, we have angular acceleration and vice versa. Whenever we have angular acceleration, we have a change in omega. They are always related. If there's no change, it means alpha is equal to 0 and vice versa. If alpha is equal to 0, there is no change in omega. Now, if alpha is constant, then we can say that omega average is equal to omega final plus omega initial divided by 2. Omega average was also equal to delta theta over delta time. What can you see here? You can clearly see the 4 kinematic equations. So I will rewrite the 4 kinematic equations again. I want you to pay attention how I write all of them. First one was delta x, I will write delta theta. The second one was v final, I will write omega final. Third one was delta x, I will write delta theta. And the last one was v final square, I will write omega final square. If you pay attention, all of them starts with v initial, so all of them will start with omega initial. And the last one is also a square, and we have a 2 here. And this one is plus omega final times delta time. This one was plus alpha times delta time. You can check the units. Now, the third one was tricky, so this one is radian. So this one is radian per second. So I have to multiply it by delta time plus, we had delta theta 1 over 2. The second delta theta has a 1 over 2. In the second one, alpha. So was it delta time square or was it delta x or whatever was it? Write the unit for alpha, which is radian per second square. So we must have delta time square. And here we have 2 and 2. We have alpha again. Was it delta time or delta x? Write the unit and you will be able to see that we have radian per second square. So we need another radian. So we need to have delta theta.
And for the missing quantities, in the first one, we don't have any alpha. So if a question didn't give you any alpha or it didn't require you to find alpha, use the first one. And in the second one, there is no delta theta. In the third one, there's no omega final. In the last one, there's no delta time. So if these quantities were not given and not required either, use the corresponding equation. When we have different points, I will choose this point as B, this point as, and I will rotate it in counterclockwise direction, and I will see that point B after a time interval comes here, point A also comes here. Now they have the same delta time, of course, so delta time for A is equal to delta time for B. And I know that the radius for A is bigger than the radius for B. B has rotated through an angle of 90 degrees. A also has rotated through the same angle, which is 90 degrees. So delta theta for A is equal to delta theta for B. And if I divide delta theta by delta time, what do I get? I will get omega. So they are same. So omega for A is equal to omega for B. And again, if I change omega for A, omega for B also change. Divide this by delta time, divide this by delta time. What do we get? We get alpha A is equal to alpha for B. We can conclude and say that every point on a rotating object has the same angular quantities except the axis of rotation. So every point has the same angular speed, angular acceleration, and angular displacement. That's all about section 1.